14 billion miles from Earth, a machine built before the invention of the personal computer is picking up something that shouldn't exist. Not a message, not a voice. Something stranger, and in its own way, more profound. The actual physical sound of interstellar space itself. A real, measurable signal rippling through the emptiness between the stars, arriving at a spacecraft that was never designed to hear it, using an instrument nobody expected would still be working this many decades later. This is the real story of what NASA has confirmed Voyager 1 is actually detecting out there, why the space between star systems turns out to be humming rather than silent, and why scientists are still trying to fully understand what that hum is telling us. Let's start with what receiving signals from interstellar space actually means in this context, because it's easy to imagine something dramatic that isn't quite what's happening, and equally easy to underestimate just how strange the real, confirmed science actually is. Voyager 1 does not have a radio receiver picking up broadcasts from some other civilization. What it has is a plasma wave instrument, a piece of scientific equipment originally designed to study the charged particle environment around Jupiter and Saturn, back when the spacecraft was still cruising through our own solar system in the late 1970s and early 1980s. That same instrument, decades later, turned out to be capable of something nobody had specifically designed it to do, directly detecting oscillations in the plasma of true interstellar space, the extremely thin ionized gas that fills the vast distances between star systems throughout our galaxy. To understand why that matters, you have to go back to August of 2012, when Voyager 1 crossed a boundary called the heliopause, becoming the first human-made object in history to leave the heliosphere, the enormous protective bubble of solar wind and magnetic field generated by our own sun that envelops the entire solar system, all 8 planets, the asteroid belt, and everything else we've ever directly explored. Crossing that boundary meant leaving the direct influence of our own star behind entirely and entering the interstellar medium, the material that exists between star systems, seeded over billions of years by the remnants of ancient supernova explosions scattered across the galaxy. For decades before that crossing, scientists had built models predicting what conditions in that space should look like, based entirely on indirect observation from telescopes here at home. Nobody had ever actually been there to check. Voyager 1's plasma wave instrument gave scientists their first direct in-place answer, and it came in an unexpected form. Beginning in 2017, researchers analyzing the data being sent back by that instrument identified something persistent, a continuous, structured signal, a low, steady oscillation in the density of the plasma immediately surrounding the spacecraft. In 2020, after careful analysis to isolate and confirm what they were seeing, scientists at NASA and Cornell University publicly described this finding using a phrase that stuck immediately: the hum of interstellar space. This wasn't a single, dramatic burst of energy triggered by some outside event. It was a constant baseline signal present in the data continuously, representing what appears to be the ordinary, standing background activity of the plasma that fills interstellar space itself everywhere all the time, whether or not anything dramatic happens to trigger it. Stella Koch-Ocker, the Cornell University doctoral researcher who led the analysis confirming the signal, described the discovery in terms that capture exactly why it matters. The interstellar medium, she noted, is like a quiet, gentle rain. Occasionally, when something more dramatic happens, like an outburst from our own sun, that quiet rain intensifies briefly into something like a thunderstorm. But underneath even the calmest conditions, there's a persistent, continuous hum running in the background at all times. That persistent signal is exactly what Voyager 1's plasma wave instrument has been picking up. A real physical property of interstellar space, not something metaphorical or symbolic, but an actual electromagnetic oscillation in the charged particles filling the void between stars. James Cordes, another Cornell researcher involved in studying this data, put the significance of the finding plainly. Before Voyager 1's measurements, scientists only had a handful of scattered data points describing the density of the interstellar plasma, mostly gathered during rare, dramatic events, when a solar outburst happened to trigger a detectable disturbance that could be measured from a distance. What Voyager 1's continuous hum detection provided instead was something scientists had never had before: a way to track the density and behavior of interstellar plasma constantly, in a steady, ongoing fashion, rather than only during brief, unpredictable spikes of activity. It transformed an occasional lucky glimpse into interstellar conditions into something closer to continuous, reliable monitoring, using a single-aging spacecraft that happened to be sitting in exactly the right and only place in the galaxy where such measurements could actually be taken. That's the real, scientifically confirmed core of what NASA has verified: Voyager. One genuinely is receiving something continuously from deep interstellar space, and it genuinely is a signal in the proper scientific sense. A real, structured oscillation in the plasma wave data, not random background noise. It simply isn't a signal in the sense of a broadcast or a message. It's closer to a spacecraft holding a stethoscope up against the actual body of the galaxy and listening to its steady, ongoing heartbeat. The story doesn't stop there, though, because Voyager 1's plasma wave instrument has also picked up far more dramatic events layered on top of that constant background hum, moments when something distant and violent sends a detectable ripple all the way out to where the spacecraft is currently traveling. When the sun produces a coronal mass ejection, a massive eruption of solar plasma and magnetic field blasting outward from its surface, that disturbance travels outward through the entire solar system, eventually reaching the heliopause and continuing on into interstellar space itself as a genuine pressure wave propagating through the surrounding plasma for months or even years after the original eruption occurred. When one of these solar-triggered waves eventually reaches Voyager 1's location, the plasma wave instrument detects it clearly, registering as a sudden, sharp spike in oscillation frequency that stands out distinctly against the steady, quieter hum running in the background. Scientists have used these dramatic events specifically to calculate the density of the plasma. Voyager 1 is currently traveling through, since the exact frequency of the oscillation triggered by a passing wave depends directly on how dense the surrounding material actually is. And what those calculations revealed genuinely surprised researchers. The plasma density measured just outside the heliopause turned out to be noticeably higher than pre-crossing models had predicted it would be. That unexpected density has led scientists to a compelling explanation. Plasma appears to compress right at the boundary between our solar system and interstellar space, piling up where the outward pressure of the sun's own solar wind meets the inward pressure of the surrounding interstellar medium, similar to the way snow accumulates in front of a plow blade, rather than simply being pushed cleanly aside. Confirming that compression effect matters directly for understanding how well protected our entire solar system actually is from galactic cosmic radiation, the high-energy particles blasted outward across the galaxy by ancient supernovae, since the density and behavior of material right at that boundary directly affects how much of that radiation manages to reach the inner solar system, including Earth. There's an additional, even stranger layer buried in this data that connects directly to Voyager 1's ongoing observations since 2020. Beyond the steady interstellar hum and the occasional dramatic pressure waves triggered by solar activity, Voyager 1's instruments have also detected a sustained, longer-term increase in both magnetic field strength and plasma density in the specific region of space it's currently passing through, an elevated reading that has persisted for years, rather than appearing as a single brief event. Some mission scientists have proposed that this could indicate Voyager 1 has entered a small ancient cloud of interstellar plasma, potentially carrying the leftover magnetic signature of a long-dead star or an ancient star-forming region that ejected this material into the galaxy millions of years before our own solar system even existed. If that theory holds up under continued observation, it would mean our entire solar system may currently be moving through, or immediately adjacent to, a genuine remnant of ancient stellar activity, a real physical structure embedded in the fabric of interstellar space that our sun's heliosphere is now interacting with directly, in ways that pre-Voyager models never anticipated needing to account for. None of this would be knowable at all without a spacecraft actually sitting out there, in that exact location, continuously transmitting data back across a gap so vast that the signal itself takes over 22 hours, traveling at the speed of light just to complete the one-way journey home. That delay is worth sitting with for a moment, because it shapes literally everything about how this science actually gets done. Every single reading Voyager 1's plasma wave instrument records has already traveled for the better part of a day before scientists on Earth ever see it, meaning the signal being described in this story isn't something happening in real time from our perspective. It's a message from the recent past of a place so remote that even light, the fastest thing in the universe, needs the better part of an entire day just to cross the distance separating us from the spacecraft currently gathering it. That distance, and the sheer improbability of the entire situation, is part of what makes this discovery so remarkable in the first place. Voyager 1 launched in 1977, designed for a 5-year mission, specifically intended to study Jupiter and Saturn, using instruments built with the electronics and engineering standards of the mid-1970s, decades before anyone seriously anticipated the spacecraft would still be operational, let alone still making genuinely new scientific discoveries nearly 50 years later. The plasma wave instrument responsible for detecting this interstellar hum wasn't specifically designed with this exact purpose in mind. It was built to study charged particles around gas giants relatively close to home. That the same instrument turned out to be sensitive enough and durable enough to still be functioning, continuously listening to the actual physical structure of interstellar space itself decades after its original mission objectives were completed, is as much a testament to fortunate engineering as it is to deliberate scientific design. And the window for continuing to gather this kind of data is closing, in a very real, physically unavoidable sense. Voyager 1 runs on a radioisotope thermoelectric generator, a nuclear battery converting the heat of decaying plutonium into electricity, and that power source loses a small amount of output every single year as the radioactive material inside gradually decays. NASA engineers have already been forced to shut down instrument after instrument over the decades, specifically to conserve what little power remains, a difficult and ongoing triage process aimed at keeping the spacecraft's most scientifically valuable systems, including the plasma wave instrument responsible for this interstellar hum detection, running for as long as physically possible. Every additional month that instrument continues operating adds more data to a dataset that quite literally cannot be replicated by any other means currently available to humanity. There is no other spacecraft anywhere near this region of space, and no funded, built, or launched mission capable of reaching interstellar space again for decades, even under highly optimistic timelines. What makes this story worth telling honestly, without exaggeration or invented drama, is that the real confirmed science here is already remarkable enough on its own terms. NASA has genuinely verified that Voyager 1 is receiving a continuous signal from deep interstellar space, a real, physical, structured electromagnetic hum representing the baseline activity of the plasma filling the space between our solar system and the rest of the galaxy, layered with occasional dramatic spikes triggered by solar storms traveling billions of miles to reach it, and an unexplained, sustained anomaly that may represent the ancient signature of a long-dead star's remnant material. None of that required embellishment to be worth your attention. It's a nearly 50-year-old machine, built with technology from another era entirely, currently serving as humanity's only working set of ears in a region of the galaxy no other instrument has ever directly sampled, faithfully sending back a steady, patient signal from a place light. Itself takes almost a full day to reach.